All right. Welcome to Crafting Interpreters in Rust. Uh, we did some stuff on chapter 10 last time, and I think there are a few small things like checking arity and stuff that we still haven't done, but I'm just going to go ahead and read chapter 11, which is about more things to do with functions, in particular, how you attach the right variables to closures, which need to be implemented a bit differently. So yeah, I will read chapter 11 first, and then we will catch up on what we want to implement. All right. So resolving and binding. Oh no, our language implementation is taking on water. Way back when we added variables and blocks, we had scoping nice and tight, but when we later added closures, a hole opened up in our formerly waterproof interpreter. Most real programs are unlikely to slip through this hole, but as language implementers, we take a sacred vow to care about correctness even in the deepest, dampest corners of the semantics. We will spend this entire chapter exploring that leak and then carefully patching it up. In the process, we will gain a more rigorous understanding of lexical scoping as used by LOX and other languages in the C tradition. We'll also get a chance to learn about semantic analysis, a powerful technique for extracting meaning from the user's source code without having to run it. So, static scope. Quick refresher. LOX, like most modern languages, uses lexical scoping. This means that you can figure out which declaration a variable name refers to just by reading the text of the program. For example, here we know that the A being printed is the variable declared on the previous line and not the global one. Running the program doesn't and can't affect this. The scope rules are part of the static semantics of the language, which is why it's also called static scope. I haven't spelled out those scope rules, but now is the time for precision. A variable usage refers to the preceding declaration with the same name in the innermost scope that encloses the expression where the variable is used. There's a lot to unpack in that. I say variable usage instead of variable expression to cover both variable expressions and assignments. Likewise with expression where the variable is used. Preceding means appearing before in the program text. Here, the A being printed is the outer one, since it appears before the print statement that uses it. In most cases, in straight line code, the declaration preceding in text will also precede the usage in time, but that's not always true. As we'll see, functions may defer a chunk of code such that its dynamic temporal execution no longer mirrors the static textual ordering. Innermost is there because of our good friend shadowing. There may be more than one variable with a given name in enclosing scopes, as in this example. Our rule disambiguates this case by saying the innermost scope wins. Since this rule makes no mention of any runtime behavior, it implies that a variable expression always refers to the same declaration through the entire execution of the program. Our interpreter so far mostly interprets the rule correctly, but when we added closures, an error snuck in. All right. So we actually talked about this before just to know how to implement something, but we only read this far in the chapter. So before you type this in and run it, decide what you think it should print. All right, so let's think. So A is in the global scope. We have closure, which says print A. We show A. That's obviously global. We set A inside the inner scope. And then we show A again. And if we're following this definition here, we need a preceding declaration with the same name in the innermost scope that encloses the expression. So I believe that that is still referring to this variable, which still has the value of global. Yeah. That's a little tricky. Okay. So if you're familiar with closures in other languages, you'll expect it to print global twice. The first call to show A should definitely print global, since we haven't even reached the declaration of the inner A yet. And by our rule that a variable expression always resolves to the same variable, that implies the second call to show A should print the same thing. Alas, it prints global and then block. Let me stress that this program never reassigns any variable and contains only a single print statement. Yet somehow that print statement for a never assigned variable prints two different values at two different points in time. We definitely broke something somewhere. In our interpreter, environments are the dynamic manifestation of static scopes. The two mostly stay in sync with each other. We create a new environment when we enter a new scope and discard it when we leave the scope. There is one other operation we perform on environments, binding a variable in one. This is where our bug lies. Let's walk through that problematic example and see what the environments look like at each step. First, we declare A in the global scope. That gives us a single environment with a single variable in it. Then we enter the block and execute the declaration of show A. All right. We get a new environment for the block. In that, we declare one name, show A, which is bound to the locks function object we create to represent the function. The object has a closure field that captures the environment where the function was declared, so it has a reference back to the environment for the block. Now we call show A. The interpreter dynamically creates a new environment for the function body of show A. It's empty since that function doesn't declare any variables. The parent of that environment is the function's closure, the outer block environment. Inside the body of show A, we print the value of A. The interpreter looks up this value by walking the chain of environments. It gets all the way to the global environment before finding it there and printing global. Great. Next, we declare the second A, this time inside the block. It's in the same block, the same scope as show A, so it goes to the same environment, which is also the same environment show A's closure refers to. This is where it gets interesting. We call show A again. We create a new empty environment for the body of show A again, wire it up to that closure and run the body. When the interpreter walks the chain of environments to find A, it now discovers the new A in the block environment. Ooh. I chose to implement environments in a way that I hoped would agree with your formal intuition around scopes. We tend to consider all of the code within a block as being within the same scope, so our interpreter uses a single environment to represent that. Each environment is a mutable hash table. When a new local variable is declared, it gets added to the existing environment for that scope. That intuition, like many in life, isn't quite right. A block is not necessarily all the same scope. Consider at the first marked line, only A is in scope. At the second line, both A and B are. If you define a scope to be a set of declarations, then those are clearly not the same scope. They don't contain the same declarations. It's like each var statement splits the block into two separate scopes, the scope before the variable is declared and the one after, which includes the new variable. But in our implementation, environments do not act like the entire block is one scope, just a scope that changes over time. Closures do not like that. When a function is declared, it captures a reference to the current environment. The function should capture a frozen snapshot of the environment as it existed at the moment the function was declared. But instead, in the Java code, it has a reference to the actual mutable environment object. When a variable is later declared in the scope that environment corresponds to, the closure sees the new variable, even though the declaration does not precede the function. All right. Okay. Persistent environments. There is a style of programming that uses what are called persistent data structures. Unlike the squishy data structures you're familiar with in imperative programming, a persistent data structure can never be directly modified. Instead, any quote-unquote modification to an existing structure produces a brand new object that contains all of the original data and the new modification. The original is left unchanged. If we were to apply that technique to environment, then every time you declared a variable, it would return a new environment that contained all of the previously declared variables, along with the one new name. Declaring a variable would do the implicit split where you have an environment before the variable is declared and one after. A closure retains a reference to the environment instance in play when the function was declared. Since any later declarations in the block would produce a new environment objects, the closure wouldn't see the new variables and our bug would be fixed. This is a legit way to solve the problem, and it's the classic way to implement environments in scheme interpreters. We could do that for locks, but it would mean going back and changing a pile of existing code. I won't drag you through that. We'll keep the way we represent environments the same. Instead of making the data more statically structured, we'll bake the static resolution into the access operation itself. Okay. Our interpreter resolves a variable, tracks down which declaration it refers to, each and every time the variable expression is evaluated. If that variable is swaddled inside a loop that runs 1,000 times, that variable gets re-resolved 1,000 times. We know static scope means that a variable usage always resolves to the same declaration, which can be determined just by looking at the text. Given that, why are we doing it dynamically every time? Doing so doesn't just open the hole that leads to our annoying bug, it's also needlessly slow. A better resolution is to resolve each variable use once. Write a chunk of code that inspects the user's program, finds every variable mentioned, and figures out which declaration each refers to. This process is an example of a semantic analysis. Where a parser tells only if a program is grammatically correct, a syntactic analysis, semantic analysis goes farther and starts to figure out what pieces of the program actually mean. In this case, our analysis will resolve variable bindings. Excuse me. We'll know not just that an expression is a variable, but which variable it is. There are a lot of ways we could store the binding between a variable and its declaration. When we get to the C interpreter for locks, we'll have a much more efficient way of storing and accessing local variables. But for JLocks, I want to minimize the collateral damage we inflict on our existing code base. I'd hate to throw out a bunch of mostly fine code. Instead, we'll store the resolution in a way that makes the most of our existing environment class. Recall how the accesses of A are interpreted in the problematic example. Okay. In the first correct evaluation, we look at 3 environments in the chain before finding the global declaration of A. Then when the inner A is later declared in a block scope, it shadows the global one. The next lookup walks the chain, finds A in the second environment, and stops there. Each environment corresponds to a single lexical scope where variables are declared. If we could ensure a variable lookup always walked the same number of links in the environment chain, that would ensure that it found the same variable in the same scope every time. To resolve a variable usage, we only need to calculate how many hops away the declared variable will be in our environment chain. The interesting question is when to do this calculation, or put differently, where in our interpreter's implementation do we stuff the code for it? Since we're calculating a static property based on the structure of the source code, the obvious answer is in the parser. That is the traditional home, and is where we'll put it later in CLocks. It would work here too, but I want an excuse to show you another technique. We'll write our resolver as a separate pass. Okay. A variable resolution pass. After the parser produces the syntax tree, but before the interpreter starts executing it, we'll do a single walk over the tree to resolve all the variables it contains. Additional passes between parsing and execution are common. If locks had static types, we could slide a type checker in there. Optimizations are often implemented in separate passes like this too. Basically, any work that doesn't rely on state that's only available at runtime can be done in this way. Our variable resolution pass works like a sort of mini interpreter. It walks the tree, visiting each node, but a static analysis is different from a dynamic execution. There are no side effects. When the static analysis visits a print statement, it doesn't actually print anything. Calls to native functions or other operations that reach out to the outside world are stubbed out and have no effect. There is no control flow. Loops are visited only once. Both branches are visited in if statements. Logic operators are not short-circuited. Okay. Like everything in Java, our variable resolution pass is embodied in a class. All right. Since the resolver needs to visit every node in the syntax tree, it implements the visitor abstraction we already have in place. Only a few kinds of nodes are interesting when it comes to resolving variables. A block statement introduces a new scope for the statements it contains. A function declaration introduces a new scope for its body and binds its parameters in that scope. A variable declaration adds a new variable to the current scope. Variable and assignment expressions need to have their variables resolved. The rest of the nodes don't do anything special, but we still need to implement visit methods for them that traverse into their subtrees. Even though a plus expression doesn't itself have any variables to resolve, either of its operands might. Okay. Just sort of letting that sink in. So blocks, function declarations. So yeah, for us, we're not using visitors yet. So we will, I guess, just make another recursive descent pass that ignores most of the types. Okay. Yeah, I don't think this will be bad. Yeah. All right. Resolving blocks. We start with blocks since they create the local scopes where all the magic happens. Okay. So here's a block statement visitor for the resolver. This begins a new scope, traverses into the statements inside the block, and then discards the scope. The fun stuff lives in those helper methods. We start with the simple one. So resolve. You just recursively resolve the list of statements in the block. Okay. These methods are similar to the evaluate and execute methods in the interpreter. They turn around and apply the visitor pattern to the given syntax tree node. The real interesting behavior is around scopes. A new block scope is created like so. All right. So when you begin scope, that means that you're putting a new hash map on the scopes stack, which we also have something like this. Lexical scopes nest in both the interpreter and the resolver. They behave like a stack. The interpreter implements that stack using a linked list, the chain of environment objects. In the resolver, we use an actual Java stack. This field keeps track of the stack of scopes currently in scope. Each element of the stack is a map representing a single block scope. Keys, as in environment, are variable names. The values are booleans for a reason I will explain soon. The scope stack is only used for local block scopes. Variables declared at the top level in the global scope are not tracked by the resolver because they are more dynamic in locks. When resolving a variable, if we can't find it in the stack of local scopes, we assume it must be global. Since scopes are stored in an explicit stack, exiting one is straightforward. Okay, now we can push and pop a stack of empty scopes. Let's put some things in them. All right, so yeah, you just move it off of the top. I guess what I'm not getting yet is where is he actually storing the results of this whole pass? Because he has a scope thing. I guess we haven't seen what resolve does. Yeah, okay. Okay, Resolving a variable declaration adds a new entry to the current innermost scopes map. That seems simple, but there's a little dance we need to do. All right. We split binding into two steps, declaring then defining in order to handle funny edge cases like this. So var a equals outer, and then you set a equals a in the inner scope. So let's see what he's talking about. So you do something between declaring and defining. Okay. What happens when the initializer for a local variable refers to a variable with the same name as the variable being declared? We have a few options. Run the initializer, then put the new variable in scope. Here, the new local A would be initialized with outer, the value of the global one. In other words, the previous declaration would desugar to var temp equals A, var A, and then A equals temp. Put the new variable in scope, then run the initializer. This means you could observe a variable before it's initialized, so we would need to figure out what value it would have then, probably nil. Oh. That means the new local A would be reinitialized to its own implicitly initialized value, nil. Now the desugaring would look like this. 3, make it an error to reference a variable in its initializer. Have the interpreter fail either at compile time or runtime if an initializer mentions the variable being initialized. Do either of those first two options look like something a user actually wants? Shadowing is rare and often an error, so initializing a shadowing variable based on the value of the shadowed one seems unlikely to be deliberate. The second option is even less useful. The new variable will always have the value nil. There's never any point in mentioning it by name. You could use an explicit nil instead. Since the first two options are likely to mask user errors, we'll take the third. Further, we'll make it a compile error instead of a runtime one. That way, the user is alerted to the problem before any code is run. In order to do that, as we visit expressions, we need to know if we're inside the initializer for some variable. We do that by splitting binding into two steps. The first is declaring it, right? Declaration, oh, I see something in chat. Yeah. Yeah, I guess, so why would it be any different in Rust? Just static typing? Or just arbitrary? It's like they just decided differently.
Well, in Rust it's useful because you can change properties of the variable. Here we change it from mutable to immutable and back.
Yeah. Yeah, I have used that. Yeah. I guess, so are they talking about only the case where you didn't? Yeah, so what's wrong with this case? I don't know why they're complaining about it. I guess because there's no point. Like, it has the same semantics in either way.
Yeah.
Okay. Yeah, that makes sense. Okay. So declaring it. Declaration adds the variable to the innermost scope so that it shadows any outer one and so that we know the variable exists. All right. So scopes.peak, that gets you the innermost scope. And then we put it in that scope. We mark it as not ready yet by binding its name to false in the scope map. The value associated with the key in the scope map represents whether or not we have finished resolving that variable's initializer. Okay. So I guess like that means like whether we finished linking it to where it's supposed to get its value from at runtime. I guess that's what an initializer would be. So after declaring the variable, we resolve its initializer expression in that same scope where the new variable now exists but is unavailable. Once the initializer expression is done, the variable is ready for prime time. We do that by defining it. All right, so you're gonna, right. You're gonna go call the initializer, whatever that means. Oh, I guess this is just that's his word for like what the value is that you're setting the variable to in declaration. Yeah, thing after the equal sign. So you go resolve that. Okay. Okay. Once the initializer expression is done, the variable is ready for prime time. We do that by defining it. All right. We set the variable's value in the scope map to true to mark it as fully initialized and available for use. It's alive. Okay. So what was the point? What was the point of that? So because this thing can throw an error when you try to resolve it, maybe? Yeah. I think the point is when this is going to throw an error. But then why wouldn't you just do that first, I guess? And then do both of these in one go. All right, I don't get it yet. I don't get it yet. All right. Resolving variable expressions. Variable declarations and function declarations, which we'll get to, write to the scope maps. Those maps are read when we resolve variable expressions. Okay. First, we check to see if the variable is being accessed inside its own initializer. All right, so how do you do that? This is where the values in the scope map come into play. If the variables exists in the current scope, but its value is false, that means we have declared it, but not yet defined it. We report that error. All right, so that would be, I guess, something like just like var a equals a, and we've declared it, but not defined it. So it would just report that statically before getting to it. Yeah. After that check, we actually resolve the variable itself using this helper. So resolve local. Okay. Now we're going to go back through that. This is when we check the innermost scope first and then go back like you would normally do, like we're doing right now. Okay. But instead of you're calling interpreter.resolve on that. So I think, yeah, resolve means what he was saying earlier, where it's almost like just looking it up in the hash map and then returning the value of like the innermost scope that contains that variable name, except instead of just returning it, you're noting how many hops away it was. And then just recording that information for later. Okay. We start at the innermost scope and work outwards, looking in each map for a matching name. If we find the variable, we resolve it, passing in the number of scopes between the current innermost scope and the scope where the variable was found. So if the variable was found in the current scope, we pass in 0. If it's in the immediately enclosing scope, 1. You get the idea. If we walk through all of the block scopes and never find the variable, we leave it unresolved and assume it's global. We get to the implementation of that resolve method a little later. For now, let's keep on cranking through the other syntax nodes. All right. The other expression that references a variable is assignment. Resolving one looks like this. All right. So resolve value, the resolve local thing again on the entire expression. Okay. First, we resolve the expression for the assigned value in case it also contains references to other variables. Then we use our existing resolve local method to resolve the variable that's being assigned to. Okay, so this is like the thing you're assigning. This is the name of the variable you're assigning to. All right. Finally, functions. Functions both bind names and introduce a scope. The name of the function itself is bound in the surrounding scope where the function is declared. When we step into the function's body, we also bind its parameters into that inner function scope. Okay. So function has a name in it. You declare and define it because you already have the function object. Or no, that happens at runtime. All right, resolve function. So similar to visit variable statement, we declare and define the name of the function in the current scope. Unlike variables, though, we define the name eagerly before resolving the function's body. This lets a function recursively refer to itself inside its own body. Oh, okay, so the recursion doesn't work unless you do the define first. Then we resolve the function's body using this. So you begin a scope, you declare and define params in a loop, you then resolve the function body, and you end scope. It's a separate method since we will also use it for defining blocks methods when we add classes later. Creates a new scope for the body and then binds variables for each of the function's parameters. Once that's ready, it resolves the function body in that scope. This is different from how the interpreter handles function declarations. At runtime, declaring a function doesn't do anything with the function's body. The body doesn't get touched until later when the function is called. In a static analysis, we immediately traverse into the body right then and there. Okay. Resolving the other syntax tree nodes. That covers the interesting corners of the grammars. We'll handle every place where a variable is declared, read, or written, and every place where a scope is created or destroyed. Even though they aren't affected by variable resolution, we also need visit methods for all of the other syntax tree nodes in order to recurse into their subtrees. Sorry this bit is boring, but bear with me. All right. I don't know if we'll bear with them. I'll just get the gist of this. So basically, you just have to call resolve. You have to do recursive descent, just like anything else. I guess what he's doing is, what he's doing is just calling resolve on anything that could contain one of the like node types that actually matters up here. And then otherwise just continuing past. So it's like the recursive structure is different. Yeah. Yeah, I think that's what he's doing. All right. So interpreting resolved variables. Let's see what our resolver is good for. Each time it visits a variable, it tells the interpreter how many scopes there are between the current scope and the scope where the variable is defined. At runtime, this corresponds exactly to the number of environments between the current one and the enclosing one where the interpreter can find the variable's value. The resolver hands that number to the interpreter by calling this. So resolve an expression with a depth. We want to store the resolution information somewhere so we can use it when the variable or assignment expression is later executed. But where? One obvious place is right in the syntax tree node itself. That's a fine approach, and that's where many compilers store the results of analyses like this. We could do that, but it would require mucking around with our syntax tree generator. Instead, we'll take another common approach and store it off to the side in a map that associates each syntax tree node with its resolved data. Interactive tools like IDEs often incrementally reparse and re-resolve parts of the user's program. It may be hard to find all of the bits of state that need recalculating when they're hiding in the foliage of the syntax tree. A benefit of storing this data outside of the nodes is that it makes it easy to discard it. Simply clear the map. You might think we need some sort of nested tree structure to avoid getting confused when there are multiple expressions that reference the same variable, but each expression node is its own Java object with its own unique identity. A single monolithic map doesn't have any trouble keeping them separated. All right, so because exprs are hashable, we can do that. As usual, using a collection requires us to import a couple of names. Yep. Accessing a resolved variable. Our interpreter now has access to each variable's resolved location. Finally, we get to make use of that. We replace the visit method for variable expressions with this. Okay, so this is in the interpreter, right? Not the parser or the resolver. Yeah. So return lookup variable with the name and the expression, which you need to look into the map locals. That delegates to this. There are a couple things going on here. First, we look up the resolved distance in the map. Remember that we resolved only local variables. Globals are treated specially and don't end up in the map, hence the name locals. So if we don't find a distance in the map, it must be global. In that case, we look it up dynamically directly in the global environment. All right, so we didn't record distance for globals, so you do that if it's null. Otherwise, you do that. All right. And then that throws a runtime error if the variable still isn't defined. If we do get a distance, we have a local variable, and we get to take advantage of the results of our static analysis. Instead of calling get, we call this new method on environment. So get at with a distance, ancestor. We don't have to, I don't think, so we're not using a linked list for this. We're just using like a vec of these things, the maps. So we'll just index into it. The old get method dynamically walks the chain of enclosing environments, scouring each one to see if the variable might be hiding in there somewhere. But now we know exactly which environment in the chain will have the variable. We reach it using this helper method. Yep. This walks a fixed number of hops up the parent chain and returns the environment there. Once we have that, get@, simply returns the value of the variable in that environment's map. It doesn't even have to check to see if the variable is there. We know it will be because the resolver already found it before. All right. Let's see. This chapter is, I guess, we can probably finish it. This is, I think, the longest and most like implementation detail oriented chapter so far. But I'll go ahead and finish it. Assigning to a resolved variable. We can also use a variable by assigning to it. The changes to visiting an assignment expression are similar. All right, so what are we doing? So yeah, okay, so everything we did with an environment before, like define and assign and stuff. Yeah, define, lookup, all of that. Always like looked at the innermost scope and then went back up to the enclosing scopes and so on. But now we always have to use this distance information that we collected. All right. Again, we look up the variable scope distance. If not found, we assume it's global and handle it the same way as before. Otherwise, we call this new method. Yep. Makes sense. Those are the only changes to interpreter. This is why I chose a representation for our resolved data that was minimally invasive. All the rest of the nodes continue working as they did before. Even the code for modifying environments is unchanged. We do need to actually run the resolver though. We insert a new pass after the parser does its magic. All right, so because it's implemented as a visitor, it's just tossed into the list of things you do. We don't run the resolver if there are any parse errors. Right? If the code has a syntax error, it's never going to run, so there's little value in resolving it. If the syntax is clean, we tell the resolver to do its thing. The resolver has a reference to the interpreter and pokes the resolution data directly into it as it walks over variables. When the interpreter runs next, it has everything it needs. At least that's true if the resolver succeeds, but what about errors during resolution? Okay, resolution errors. Since we are doing a semantic analysis pass, we have an opportunity to make LOX's semantics more precise and to help users catch bugs early before running their code. Take a look at this bad boy. All right. So, okay. We do allow declaring multiple variables with the same name in the global scope, but doing so in a local scope is probably a mistake. If they knew the variable already existed, they would have assigned to it instead of using var. And if they didn't know it existed, they probably didn't intend to overwrite the previous one. We can detect this mistake statically while resolving. All right. So this is in the resolver pass. If you've already got, one second, I think I might be getting a call. I just need to check. All right, I'm good. Okay. When we declare a variable in a local scope, we already know the names of every variable previously declared in that same scope. If we see a collision, we report an error. Okay, here's another nasty little script. Return at top level. This executes a return statement, but it's not even inside a function at all. It's top level code. I don't know what the user thinks is going to happen, but I don't think we want LOX to allow this. We can extend the resolver to detect this statically. Much like we track scopes as we walk the tree, we can track whether or not the code we are currently visiting is inside a function declaration. Yep, so just adding some more just bookkeeping to the function, to the resolver pass. All right, instead of a bare Boolean, we use this funny enum. So function type is either none or inside a function. Seems kind of dumb now, but we'll add a couple more cases to it later, and then it will make more sense. When we resolve a function declaration, we pass that in. Okay. Over in resolve function, we take that parameter and store it in the field before resolving the body. Okay, so resolve function. Guess, what is this? Where does that come from? All right. We stashed the, oh, is that, yeah, that's global. I see. Yeah, okay. That's like some mutable state that's in the for the entire pass. Yeah. Okay. So you set enclosing function to current function, and then you set current function to the function type that you call when you call resolve function, which is always just you're in a function. All right. We stash the previous value of the field in a local variable first. Remember, LOX has local functions, so you can nest function declarations arbitrarily deeply. We need to track not just that we're in a function, but how many we're in. We could use an explicit stack of function type values for that, but instead we'll piggyback on the JVM. We store the previous value in a local on the Java stack. When we're done resolving the function body, we restore that field to that value. Now that we can always tell whether or not we're inside a function declaration, we check that when resolving a return statement. All right, so if you're not in a function, then you throw an error. Neat, right? There's one more piece. Back in the main locks class that stitches everything together, we are careful to not run the interpreter if any parse errors are encountered. That check runs before the resolver so that we don't try to resolve syntactically invalid code. But we also need to skip the interpreter if there are resolution errors, so we add another check. You could imagine doing lots of other analysis in here. For example, if we added break statements to locks, we would probably want to ensure they are only used inside loops. We could go farther and report warnings for code that isn't necessarily wrong, but probably isn't useful. For example, many IDEs will warn if you have unreachable code after a return statement or a local variable whose value is never read. All of that will be pretty easy to add to our static visiting pass or as separate passes. But for now, we'll stick with that limited amount of analysis. The important part is that we fixed that one weird, annoying edge case bug, though it might be surprising that it took this much work to do it. Okay. Cool. Wow, that was a lot of reading. So that's chapter 11. Do people have questions or, sort of want to know more about the context of how we got to this chapter? It's kind of technical. All right. If not, I will go over to the code and try to think about how we're going to do this additional recursive pass. So we have a place to slot it in here. When we run a program, we're going to do the variable resolution pass. And then I suppose we'll pass in the so we have the env stack. We'll probably just end up passing in just more variables. Maybe what we'll end up. Okay, Michael, do you think it's a good idea to just put all of the pieces of state in one structure? Or I guess actually no, the static analysis stuff is not going to need to be mutable. So we want a mutable environment stack and then an additional parameter, which is like the variable resolutions.
Can we modify AST? We can initialize it with every variable we can initialize with the field and start with none and do a pass.
Oh yeah, sure.
Some.
That's fine. So yeah, I like that idea. So I guess he mentioned that a lot of compilers do that, but that he is mapping it separately. Okay. So
I can merge this with this interlinear. Yeah, it sounds good. Possibly. Yeah, I mean there may be some odd cases. I haven't looked at it all really.
Resolution distances. And I guess the only other thing, the only other state that results from this resolver pass is. Wait, is there any? I think that's it. Because everything else here is like checking for errors, like the return at top level thing. Yeah, I think that's it right now. Yeah, okay. So first thing to do is just modify the AST node types to have a distance in it. That's fine.
Very good.
Okay. Where does this go, I guess? It'll be somewhere like here. it's, yeah, because, okay, he didn't do it that way. Oh, I guess it's expressions, right? Because his hash map was based on expressions.
Just a bit left.
So all the expressions need a resolution distance, I think. So maybe do we need to make like separate this and make it a struct? Which has an expression type in it. And then a distance. I don't know.
Just a bit left. Just a bit left.
I don't, I mean, the other thing would be putting the distance in all these variants. So it seems better to just do this.
We don't really need all of them, do we? We need identifier. We
Okay.
don't need like numeric literals, string literals, nullable, this.
Does this, I guess the identifier for the class is what's going to keep track of it for this. How about that? I think we also need for function. Or let me see.
Well, a few places, but not all of them.
Yeah. Okay. Cool. So just keep it as this. That's fine. And then we'll do this kind of thing.
I see that when the IDEV is 0,
Okay.
it doesn't change the dev. Is that right? When the IDEV is
All right.
empty.
Maybe functions. I don't know yet. I guess that would just depend. I'll look back next time to see where he put stuff in, like for which expression type, and then only add it to that. And then otherwise, this is the end of the session, end of the time. So anybody have any last minute questions, comments, anything? Cool. I will stop recording.